Hello. In the previous lecture, I have explained the basic idea of a hypothesis test. I interpreted hypothesis testing as a kind of testing on assumption of the model. And the key idea is we need to identify the relevant parameter, the parameter that is used in the hypothesis. The parameter must be identified without using the hypothesis in order to test the hypothesis. That was just conceptual approach, and it is related to a lot of different contexts in statistics and econometrics. Especially, we are interested in comparing different models, which model is better, or and which model we need to choose like that. So specification test, model selection, variable selection, functional form selection models, all of these all of these theories are related to some kind of hypothesis testing. And I gave you a broad general framework to understand that. And today I'm coming back to statistics a little more, and I will introduce the chi-square distribution first. Of course, I assume that, as before, I assume that you understand like the basic theory, like t statistic, what is a t statistic, and what is a standard normal distribution, and things like that. So let's start. Suppose that z is a scalar random variable, and it is a standard normal distribution. So normal distribution mean zeros, variance 1, and then z squared is another scalar random variable, and we define this to be the chi-square distribution. But we are like we say this has a parameter of 1. We are going to generalize the parameter in later, and the name of the parameter is the degrees of freedom. Like normal distribution has two parameters named mean and variance, and the chi-square distribution has one parameter named the degree of freedom. So in this case, the degree of freedom is 1. And obviously, because it is squared, obviously it is always positive. So all the probability is put on positive side. And if you are curious, you may just check Google or Wikipedia how it looks. Like so. Is it 0? And then it looks like this. Have a long tail. And now we are going to generalize this. Now suppose that there are k independent standard normal random variables. There are k variables, z1, z2, up to zk, and each of them, z1 is standard normal, z2 is standard normal, zk is also another standard normal distribution, and each of them, each pair of those random variables are independent with each other. Then, in this case, we are going to define this squared sum, z1 squared plus z2 squared plus zk squared. Then it is another scalar random variable, and then we call this chi-square distribution with parameter k. So the degrees of freedom is now k, because k number of standard normal distributions are added, squared and added. So the degree of freedom is k. Or alternatively, you may understand this in this way. So if you define a random variable x as a vector of these k random variables, then the k-dimensional vector x follows, it's a column vector, it follows a standard normal distribution. So k-dimensional standard normal distribution is defined it this way. So k-dimensional standard normal distribution is mean 0, and variance is a k by k identity matrix. So the diagonals are 1 and the other off diagonals are zeros. And then this squared sum of squares can be written as x prime x. It's in the vector notation. X prime x is it is the sum of squares. And then simply in the vector notation, x prime x follows chi-square k. K is the degrees of freedom, right? Right. So we just defined chi-square simply using standard normal distributions. So then now we may generalize this definition to start from non-normal, non-standard normal distributions. Like for example, if you have a general uh, normal distribution with mean mu and variance sigma squared, and then obviously x minus mu over sigma is standardized value of this normal variable. So this standard normal distribution variable squared will be chi-square 1. So it follows directly from the first definition. X minus mu over sigma is standard normal, therefore its square is chi-square distribution. And in k-dimensional case, say X is now multivariate normal distribution with general mean and general variance matrix. Mu is k-dimensional column vector, and sigma, capital sigma, is k by k dimensional variance matrix. It can take any form, but because it is a variance matrix, it is always symmetric and semi-positive definite. And then if it is non-singular, so by the way, variance matrix is non-singular if the k random variables does not have multicollinearity problem. So I'm not going to prove that here, but like for let's say sigma is the variance of k dimensional k random variables. If this variance is singular, if it's not invariable, which that means the k random variables have a multicollinearity relationship. So if they are not multicollinear with each other, the variance matrix will be always non-singular, right? So it is not far, it is not restrictive. So we are simply assuming full rank condition among these k random variables, and then if it is non-singular, we may decompose it to sigma 1 over 2 and the sigma to the exponent of 1 over 2. So sigma square root of sigma, square root is now in metric sense, in matrix notation. So sigma to the exponent of 1 over 2, and that is also invariable. So we may define sigma to the exponent of minus 1 over 2. So for these to be well defined, sigma must be non-singular. In scalar case, if you interpret this as a scalar, one number, then non-singularity can be interpreted as non-zero. So if this sigma is non-zero, so if sigma squared is not zero, then you may standardize like this by dividing x minus mu by sigma. Same thing. If sigma is non-singular, you may multiply this. So intuitively speaking, this corresponds to non-zero when the variance is one-dimensional, but not exactly the same as like in matrix notation. And then this is the standardized version, generalization of this. We generalize this standardization to this way. Remember, here there is no sigma squared here. We had sigma squared in one-dimensional case, but there is no square here. So that's a little bit inconsistency in the notation. So be more careful. We usually write it this way. I don't like this inconsistency. I have no power. And after the standardization, we have another standard normal distribution, multivariate standard normal distribution, k-dimensional standard normal distribution. Then following this rule, this standard normal distribution, standard normal vector prime, the standard normal vector follows chi-square k. And if you read it more carefully, you can deduce that the x prime x something prime something can be written in this way, and it's called the quadratic form. It is called quadratic form because conceptually it is equivalent to sum of squares, or in a more compact interpretation, it can be understood as a square. So basically, everything is coming from square. So square is generalized to vector multiplication, x prime x in vector case. So, and when you have non-standard variance matrix, you have to include the inverse of variance in between x prime x. So that's a natural generalization, and so it's the generalization is also called quadratic form. And that's what we are going to use. We are going to rely on this quadratic form in this chapter, throughout this chapter. And then we are going to apply the result, this definition. So far, it is kind of just a definition. The definition can be applied like this. Suppose that a sequence of random vector, xn. So xn is xn converges in distribution to normal distribution with variance v, and it is non-singular. Then the quadratic form can be written in this way, and it converges in distribution to chi-square k. Right? Exactly, this is the same form. We are using the same form, except that the mean is 0. And the variance, we replace variance as a consistent estimator for the variance. We do not need to know the true variance, but we just need another variance matrix that converges to the true variance. Then you may have this convergence, which is also very intuitive result. So then, if you plug this in, so this is, why this is important. This is the estimation error. Then estimation error follows a normal distribution, and you need to know the asymptotic variance. Then you may convert that to quadratic form, and then that follows a chi-square distribution. So we are going to use this theory a lot, and why do we need it? Let's think about this. So I said it is very important in hypothesis test because it's the generalization of t statistic. T statistic. I assume that you understand the t statistic, t test mechanism, and t statistic, and how it works, and how you derive it, and when you apply it, blah blah blah. That should be, I teach that for undergrad students, so yeah, you should know that. Anyhow, think about this. When you want to test on equality for a single parameter beta 1, then our hypothesis testing can be simply implemented in this way. Estimate beta 1, estimate the parameter you are testing, and then calculate the distance between the estimate. So this is your estimate, the data, estimate from the data, and your hypothesis. Hypothesis does not use the data. It is simply your hypothesis. I don't know why you believe beta 1 equals to 1, maybe economic theory. Anyhow, we are comparing. Is there any difference? How different the data, what the data tells you, and what your hypothesis tells you, and that's this distance. Beta 1 had -1. The bigger the difference is, the more discrepancy between the data and your belief, which means your belief is more likely to be wrong. That's the rationale. So the distance is our main focus, and the distance will be standardized, should be standardized by the standard error. Just simply divide it by standard deviation of beta 1, the estimate, the standard error of the estimate. And then we know that this, so this is defined as the t statistic, and the t statistic for this test, for this null hypothesis, and this t statistic follows a standard normal distribution. So that's the like converges in distribution to standard normal distribution. And then, as I said, we are interested in this distance. So t is a standardized difference between the data and the hypothesis. So we are comparing the distance. So if your hypothesis equals to the data, is consistent with the data, the t statistic will be close to 0. But if t statistic is too much negative or too much positive, then it means that the distance is large. So you have to reject the null hypothesis. So the critical value is chosen based on this rationale. The absolute value of the t. So the absolute value can be understood as the distance between 0 and t, right? Like, so whether, regardless of the sign, so whether it is positive or not, absolute value of t is the distance. And also we use the distribution theory, standard normal distribution. So based on these two, we choose the critical value like this. If the distance is larger than a certain point, you reject the null hypothesis. We are going to generalize this idea to multiple dimensional case. However, it is not straightforward. Let's think about this. We have a null hypothesis about two parameters, beta 1 and beta 2. Beta 1 equals to 1, beta 2 equals to 2. And then, following the same logic, you estimate beta 1, beta 2, and calculate the difference between your estimate and the hypothesis. So you can think about vector beta 1, beta 2, estimate, and 1 and 2 as a vector, two-dimensional vector. Their difference. So their difference can be written in this way as a vector. And so this is the difference between your hypothesis and your data. And the smaller the distances, the difference is, your hypothesis is likely to be true. And we standardize it. Standardization goes like this, where V is the variance matrix, asymptotic variance, or whatever variance, reasonable, consistent estimator for the variance. Then after the standardization, the problem here is we need a distance of this, but this is two-dimensional vector. So taking distance in one-dimensional was simply taking the absolute value. But what is the generalization of taking on absolute value? That is, look at this. So the distance must be calculated this way by Pythagoras theorem. Pythagorean theorem tells you the vector distance is calculated this way. So even if you have more than 2 dimensions, still the formula is the same. This is the standard Euclidean distance. And then ignoring the 1/2, the exponent, we are simply taking this part, which is still which is kind of squared distance. Then we use the quadratic form. So this one, v prime v, is this part. So f is the squared distance. Square distance, I do not take the exponent of 1/2. So this is the square distance between your data and your hypothesis. So put it like more rigorously, like still roughly speaking, F statistic is the squared standardized difference between your data and your hypothesis. So if the distance is close to 0, don't reject. But if the distance is too large, you reject. And then so anyhow, it is some kind of distance. So you reject if the distance is too large. Then how large is too large? You need to choose that from the chi-square distribution. We know how this guy is distributed. We know this guy will converge to chi-square 2. Then you can choose the critical value in the same way. So as you can see, the major difference is coming from how you measure the distance. Measuring the distance in one-dimensional is pretty simple, but measuring the distance in two-dimensional, two or high-dimensional vector requires quadratic form. And taking the square root is if you take the square root, then you get the true distance, but that complicates your algebra. So usually the square root is not taken. Okay, we are going into the main part of the hypothesis test. So I'll continue that in the next video. Bye, see you later.